Hello, my name is Prateek Sharma, and I am very excited to talk about our paper on modeling the temporally constrained preemptions of transient cloud VMs. This is joint work with JCS Kadupitige and Vikram Jadhao. So, transient cloud VMs like EC2 Spot instances, Google Preemptible VMs, and Azure Batch VMs are extremely low cost and a very popular option to reduce the cost of your cloud application. Unfortunately, these transient VMs can be preempted and revoked unilaterally by the cloud provider, and so the applications have to deal with sudden fail stop failures. So, the central challenge in transient computing is how to mitigate these preemptions. And past work has focused on two main techniques. The first is to use some kind of fault tolerance, like periodic checkpointing or migration or replication, to recover from these preemptions. The second technique is to carefully select the VM of a particular type or location which has the specific preemption characteristics that are suitable for the application. So, both these and other techniques rely on a sound understanding of preemption characteristics. That is, they require a model of when and how frequently the preemptions occur. For example, the frequency of preemption of a transient VM can be used to derive an MTTF or mean time to failure of that particular VM and hence the application. This MTTF can then be used to derive an optimal checkpointing frequency that minimizes the total expected cost and running time of running the application on transient VMs. So these kind of preemption models have largely been developed for EC2 spot instances. So spot instances have a dynamic price which is based on roughly the market supply and demand conditions. And spot instances historically were revoked if the spot price crossed the pre-specified bid price. So importantly, spot prices are public, so you can download spot prices of all different types of spot instances, analyze them, and come up with a preemption model. So this availability of spot prices and the popularity of spot instances led to a large number of preemption models being proposed and developed, and this preemption data could then be used to build smart systems that optimized the cost and performance of a large number of different applications. So this work is not about EC2 spot instances. Instead, we ask the question, what about the preemption characteristics of other types of transient VMs? So in particular, we focus on Google's preemptible VMs. These preemptible VMs have two interesting features. First, they have a flat price, so the price-based approaches are not applicable. And second, they have a maximum lifetime of 24 hours. That means that the cloud provider will forcibly preempt any preemptible VM which has reached the 24-hour mark. And it can, of course, preempt it at any point within this 0 to 24-hour interval. So we call these as temporally constrained preemptions. So in this work, we are interested in answering four research questions. So first, we want to see if Google preemptible VMs have different preemption characteristics from the previously studied spot instances. And if they do have different characteristics, we want to know what is the impact on application performance and cost. The third question that we're interested in is, can we develop a preemption reliability model for temporally constrained preemptions? And can we use this model to develop policies for checkpointing and scheduling, which are required if you want to make good use and efficient use of cloud transient VMs? So, in order to answer these questions, we use an empirical approach. We collect preemption data by launching a large number of VMs. We then develop a probability model which captures the preemption characteristics, using which we develop checkpointing and scheduling policies and we implement these policies in a new software framework called SciSpot, which is specifically suited for running scientific computing applications at low cost on Google Preemptible VMs. So, to recap, our goal is to obtain a better understanding of the preemption characteristics of Google's preemptible VMs. However, this is challenging because of two reasons. As I alluded to earlier, these preemptible VMs have a flat price, so you cannot use any dynamic pricing signals. And the second reason, which is applicable across cloud providers, is that cloud providers don't expose any information about uh, when and how frequently these preemptions will occur. So we require an empirical approach. So we ran a large number of preemptible VMs and recorded when they were preempted. So we ended up launching more than 1,000 VMs across geographical regions with VMs of different number of CPU cores and memory sizes at different times of day, running different workloads, etc. And our complete data set is available at this URL if you want to analyze it. So after launching and running these thousands of VMs, what did we learn? So we are most interested in understanding when the preemptions occur in the 24-hour interval. So this graph shows a CDF of when the preemptions occur on the y-axis, and the x-axis is the time to preemption. So interestingly, this preemption behavior has some interesting characteristics. So note that the preemptions are not uniformly spread out across the 24-hour intervals, but instead have these three distinct phases. So in the first phase, we will see a large number of VMs getting preempted. So for example, for this particular VM type, in less than 4 hours, more than 40% of the VMs are preempted already. Then the VMs encounter a second middle period, which is characterized by low preemption rates. So VMs that survive this initial high preemption rate period enjoy a relatively low probability of preemptions. For example, even till the 20-hour mark, only less than half the VMs are preempted. And finally, near the deadline of 24 hours, all the VMs must be preempted, and so we see a very sharp increase in the failure rate. So another way to look at this is to plot the slope of the CDF, which is the preemption rate or the preemption probability distribution. So if you do compute the slope of the CDF, we get something like this. So we have a high failure rate or a high preemption rate at the start, followed by a low preemption rate period, and near the deadline we see a sharp increase in the preemption rate again. So this is a classic two-sided bathtub failure rate curve that is observed in Google's preemptible VMs. So our empirical analysis shows that this kind of bathtub preemption behavior is fairly general to different types of Google's transient VMs. So the figure on the left here shows the preemption characteristics of VMs with a different number of CPUs and memory. They all have the bathtub shape, but the exact characteristics of VMs of different types are slightly different. So for example, the black curve corresponds to the preemptions of the VMs with 32 CPUs, and that those VMs are preempted more during their early phase as compared to some of the other smaller VMs. The same behavior is also seen at different times of day. So the figure on the right shows the CDF of the preemptions for VMs launched during the day versus the night, as well as VMs running some workload and idle VMs that are not running any computation at all. So in all the cases, we see these sort of three phases in a VM's life. Okay, so now Once we have the empirical data, the next step is we would like to have a probability model that helps characterize these observations. So conventionally, for modeling hardware and even transient VMs, the memoryless exponential distribution has been used. Right? This has very nice properties. There's a constant failure rate, which allows us to compute and use the MTTF for various policies. So we try to fit the classical exponential distribution to the data that we have. This is from the smooth line here. And as you can see, it is not able to capture the distinct phases and not able to model the data properly. Right? And the reason is that the exponential distribution assumes a constant failure rate. And in our case, we have these three different preemption phases and the temporal constraint. And the memoryless models are not applicable in this particular setting. We also looked at some other probability distributions. So the Weibull distribution, for example, is well known to model bathtub failures, and we tried to see if that will provide us a suitable model. So the Weibull distribution here is shown on the blue line, and it does fit the starting part of the VM's life better than the exponential distributions, but again, it's not able to capture all these three phases. Similarly, we also looked at some other distributions from other domains. So for example, the Gompertz-Makeham distribution is popular in actuarial sciences, where you want to capture sort of early infant mortality, which is high, then a fairly low mortality rate during the Middle Ages, and then an accelerating aging effect as people get older. So that Gompertz-Makeham distribution is shown by the dotted line here, and again, it's not able to capture and fit the data that we have. And again, in all cases, the reason is that because we have this sharp temporal constraint of 24 hours, it's very challenging to fit sort of existing failure models. So we had to come up with our own model to capture these three phases. So our intuition is we want to use two separate and distinct failure processes that are active at different times during a VM's life, right? So during the first and the middle parts, uh, we can see that the classical exponential distribution can probably work. And in the latter part, when you reach near the deadline, you need a positive exponential distribution to account for this steep increase in failures. So our model uses these four parameters in order to fit the preemptions that we see for Google Preemptible VMs. So this is a CDF of our model. So as you can see, in the first part, we use a conventional exponential distribution with a rate of tau 1, which captures the rate of the initial preemptions. Second, because we want to capture the deadline effect, we increase the failure rate by a positive exponential rate of tau 2. Right? However, this extremely high exponential rate is applicable only towards the end near the deadline. So we want to bias that and have an activation time denoted by small b, which captures the time at which the steep increase in failures or preemptions start to kick in near the deadline. And this is close to 24 hours. And finally, we want to normalize it so that f of 0 is 0. And so we have a scaling constant, a. So we fit this model using standard least square techniques, and that is shown by the black line here. And as we can see, it's able to fit all the three phases fairly well. And our paper shows that it's also able to capture the preemption characteristics of different types of VMs and different temporal domains. The good thing about this is our model is that it is differentiable everywhere. So we can differentiate it with respect to time and get the probability density function. And if you plot this, we get the bathtub shape that we saw earlier, which is shown by the black line here. Okay, so now that we have a model, the next question is, what can we do with it and what can we learn from it? So one interesting thing that we observed is that Bathtub preemptions are very different from uniform preemptions. So if the VMs were uniformly preempted during a 24-hour interval. So this figure shows what is the expected increase in the running time of a job because of job restarts because of preemptions, right? And the black line shows that increase in running time for uniform preemptions, and this is quadratic in nature. The x-axis is the job length. So this makes sense because the longer the job, the more likely it is to encounter a preemption and the more amount of work that you have to recompute. The red line shows this expected increase due to preemptions for the Bathtub preemption that you observed. So interestingly, for short jobs of less than 5 hours, they encounter because they encounter these early preemptions. Their expected increase in running time is slightly higher as compared to the uniform preemptions. But for longer jobs, for jobs more than 5 hours, the Bathtub preemptions are significantly better for applications because if preemptions occur, they occur at the start of the job and the amount of work that you have to recompute is much smaller. So a simple policy, if you want to use Google Preemptible VMs, is start the VM, let it sit idle, let it mature, and then start running the job. So we also developed, based on the earlier insight, a job scheduling and VM reuse policy. So the scenario here is that you're running a sequence of jobs, right? And on an existing cluster of preemptible VMs. So the question is, when a new job arrives, do you continue running on an already running on an old VM, or do you terminate that old VM and start a new VM to run this job? And the trade-off here is interesting because a new VM has a high initial preemption rate, but if the job survives this high rate, it will enjoy relative stability. But reusing a VM can also provide low failure rates. But if the job is long, then it has a risk of encountering the high preemption rate towards the end of the VM's life. So what we do is we compute the expected running time of the job, assuming that it encounters one failure. So capital T is the running time of the job without failures, and we compute the increase in running time as per this equation. Small s is the current age of the VM, right? How long the VM has been running for. So we compute this value for two values of s, the current age, e of t of s, and for a new VM for that particular job, so e of t of 0. And whichever case yields the lowest expected running time, we pick that scheduling decision. The other scenario and policy in which our model helps is that you can use a model to come up with an optimized checkpointing policy for these kind of bathtub shape preemptions. So conventionally, a classic Young Daly approach is used, which has uniform checkpoint intervals, which is shown by this equation here. In our case, the preemption rates are not uniform, and so this periodic checkpointing is not ideal. So we developed a dynamic programming approach that does this sort of non-uniform checkpointing by using it uses the length of the job and when you start the job. And the output is the time steps in terms of wall clock time or for when the checkpoint should be taken in order to minimize the total expected running time in the presence of failures. And the full details about how we compute this are in the paper. So we implemented our policies in a new software framework called SciSpot, which is a system for running scientific computing applications on Google Preemptible VMs. And it integrates with Slurm and is especially well suited for running these sort of large scientific simulation workloads that do large parameter sweeps. Because of this, you essentially get a bag of jobs, that is, jobs that have fairly similar parallel scaling and running time characteristics, which helps with the implementation of our policies. So we use SciSpot to sort of answer two main questions. What is the effectiveness of our model-based scheduling and checkpointing policies? And what is the performance and cost of running scientific simulation applications? And we use three scientific simulation applications from physics. So the first thing we want to see is what is the reduction in the probability of job failure, right? Because of our VM reuse policy. So we show the job failure probability for jobs of different length, uh, and we compare with a memoryless policy that is not aware of the Bathtub preemptions. So this is a classical exponential distribution that is shown by the black line here. And as you can see, for increasing job lengths, using our model-based policy, we can reduce the job failure probability by up to 3 times for jobs of certain length. And in all cases, our policy yields lower failure rates compared to the current memoryless distribution models. We also evaluated our checkpointing policy, and in this case, we are interested in what is the expected increase in the running time because of the frequent checkpointing overhead. And so in this figure, we are showing what is this expected increase for a job of 4 hours, and our policy is shown in black, and it has a significantly lower increase in running time because it checkpoints based on how likely and how frequent the preemptions are actually likely to occur. And finally, if we look at costs, we are able to reduce costs by 5 times compared to running on on-demand VMs. We also observed a very small, only a 3% increase on average only a 3% increase in running time due to preemptions. And this is because of two reasons. One is that if a preemption occurs, it's likely to occur at the start. And so if you have to recompute uh, because of the work lost, the amount of work that you recompute is much smaller as compared to what you would expect if it was uniformly distributed. So there are sort of two main areas of future directions or two main concerns. We can always come up with a simpler model for modeling these constraint preemptions. So we can fit a phase-wise model with an exponential distribution on a straight line, for example. I think the second common concern is, what if the preemption characteristics change? So I want to emphasize that our focus has been on trying to study the fundamental characteristics of temporally constrained preemptions as a general new type of transient VM. Right? And the current model we have shown to be is quite robust, again, as long as the general sort of bathtub shape is maintained. And using the model, we can also detect sort of model drift if the specific models change. For example, if some VMs have a higher rate of preemptions than current, so we can detect these changes. And finally, I'd like to sort of emphasize that sudden changes in cloud platforms are a common threat to validity that is shared by most cloud research, and this work is also susceptible to it. So to conclude, I talked about Google Preemptible VMs that have a unique characteristic that they have a maximum lifetime of 24 hours. So these kind of temporally constrained preemptions are an interesting new type of transient resource availability. We conducted a large empirical study of preemptions, and we showed that the failure rate is bathtub shaped, and all our preemption data is available online. We use this preemption data to develop a new failure model that is able to capture the preemption characteristics of different types of Google VMs. And using this model, we developed scheduling and checkpointing policies that help improve job running times. So thank you for listening. I'll be happy to take any questions now or later.